understand is that everything around us is chemistry. Okay, now basically talking about the human body, okay, or the most complex creation of God. Okay, now this happens to be a combination of various elements, okay, that is the carbohydrates, the proteins, the fats, vitamin, mineral, everything is chemical in nature. So our human body is a combination of various elements existing around us. Okay, now talking about respiration, okay, carbon dioxide and oxygen. We intake oxygen, we give out carbon dioxide. Now that's again a concept that is clearly understood with respect to you know reactions or chemistry. Basically, it's a process in which the energy gets broken down into the simpler absorbable forms, and energy is getting released. If we talk about the concept of like and dislike, this is governed by again a chemical called dopamine. Okay, you see a car moving on the road and you feel that you must have it, or you see a super bike moving, somebody riding out and you feel that you should have it, or you wish to have that thing. Anything that makes you happy or gives you the desire to have that substance, it's basically governed by a chemical called dopamine. So we understand that our interactions, okay, in nature are all related to chemical. Okay, and then going down to the most basic one, the digestion, the concept of absorption and assimilation happens to be related to chemistry again, because the manner in which the complex food gets broken down into the simpler ones, okay, is again related to chemistry. Now going down further, we have so many different elements, students, okay, so many different elements being discovered over the years, okay, each element having a different physical and a chemical behavior, nature, property, okay, manner of existence in nature. So what makes it so essential, okay, to classify it? Why do we emphasize on this arrangement, or this regulated manner and pattern of arrangement? There has to be some reason behind it. So why do we need to classify the elements? Okay, now talking about the early 1800s, okay, we had very few elements known and discovered. There were around 31 elements known to us, but as time progressed, the researchers, the chemists, the botanist, okay, or the scientific fraternity discovered, and the number grew up to almost 63, okay, in a span of around 60 years, 60 odd years, the number was growing, okay. So as the discovery of elements, continued, the need for a better arrangement, okay, for a better assortment was felt. Okay, now uh, as on date, we have around 118 elements known to us, which have been arranged in a proper manner in what we call as the long form of the modern periodic table. But what we see today in the long form of modern periodic table was not the first one to be formulated. Okay, there were many attempts of proper classification made by quite a few scientists. Okay, some succeeded, some did not. Everyone succeeded in their own ways, and over the period of years, we sorted to the most regulated, I would say the most disciplined and the most uniform pattern of arrangement, okay, of elements. Okay, so that's called the long form of the modern periodic table. We'll be seeing that in detail as we move further. Okay, I'm sure you all must have heard and read these things in your junior classes. So this is just a quick brush up to what you already know. And as the lecture will proceed, of course, you will get some deeper insights about the topic. And so every element, as I was saying, has its own importance. Okay, some of them are useful while others may be harmful. We should know what happens to be useful to us and what happens to be harmful. Quite of means everyone around us is. We have been hearing about this element called hydroxychloroquine these days. This also is a chemical quite useful to us in this case of a global pandemic that each one of us is suffering through. We have been restricted at our homes, and this chemical, okay, the hydroxychloroquine, it's actually a combination of carbon, hydrogen, nitrogen, oxygen, and the sulfuric acid. So it's actually hydroxychloroquine hydrogen sulfate. It's an interstitial compound, okay, and that's how we are bringing the same elements put to use, and that's helping us to get rid of this this notorious virus, I would say, that has held everyone captive at home. So every element influences us. It influences our existence, our surroundings. The more aware we are, the better we can put it to use. Okay, to put it in very simple words, students, our nature, our existence, the earth, our atmosphere, it's all of these elements, okay, existing in a different pattern and helping us in some or the other way. So it's all a combination of these elements, okay, which we see in the periodic table, that is around us in different forms and influencing us. So I hope the need for classification is understood to everyone, and those who wish to must have noted down a few of the important points as to 31 elements known earlier, the number growing up in the 1800s, and as on date we have 118 elements known to us. Now, taking things ahead, okay, I would like to stress on this thing that a classification becomes necessary in order to understand the nature. Now, what you look on the screen is sodium. You would be surprised to know that this sodium, which happens to be a component of what's called the sodium chloride, or the salt, or the table salt, or the common salt that we use in our home on a regular basis, this burns at a temperature of 22 degrees Celsius. To put it in Kelvin, it's 295 Kelvin. Okay. Now, Kelvin scale is another scale of expressing temperature. Okay. So you add 273 to the degree Celsius value to get the temperature in Kelvin. I repeat, we add the value 273. Okay, to your degree Celsius to get the temperature in Kelvin. Now this sodium, okay, it burns at a temperature of 22 degrees Celsius. That happens to be our room temperature, or even slightly lower than that. The same chlorine, which is a component of your sodium chloride or the rock salt, it happens to be a poisonous gas. Okay, chlorine, if you inhale it in small quantities, no one should, but in case if accidentally somebody comes in contact with chlorine, okay, this will give rise to irritation of your eyes, your nose will start watering, your head will start paining. In slightly higher doses, it may give rise to conditions of coma, and even chlorine happens to be fatal in cases where the exposure to chlorine is very high. Okay, chlorine, we all know, is also a component of chloroform. Okay, chloroform in very minute doses in the earlier days was used in the hospitals and surgeries as an anesthetic, but later on, due to its harmful effects, it got replaced by other advanced combinations of chlorine, which are now used as anesthetics. Okay, but this, to everybody's surprise, sodium and chlorine, it combines to give us what's called the salt, the common salt or the table salt, which we use at our home. It's a daily diet component. Okay, so if we talk about the nature, independently, sodium is behaving in a different way. Okay, on combining with chlorine, the sodium again behaves in a different way. Okay, so it's important to understand the nature and the manner in which a particular element is existing. A detailed explanation and a detailed understanding to this becomes very easy when we refer to what's called our periodic table. Now, before we actually go to the most advanced, okay, and the universally accepted form of the periodic table, that's the long form of the modern periodic table, we will just glance through the theories in the past that, made an attempt at classification but failed. Okay, now to put it, it was the very first one of the most primary methods of classification was given by Prout. That's called the unitary theory. Okay, then the other one was the Daubernier's triads. Okay, then there was the Newland's octaves, and there was the Mendeleev's classification. So talking about the Prout's hypothesis, okay, the Prout's hypothesis. Now this man correlated everything to hydrogen. Okay, according to him, every element had a component of hydrogen in it, or we could say it in the other ways, that every element was a combination of a varied number of hydrogen atoms existing. But this was unfortunately wrong, because if every element had hydrogen in it, the behavior of every element would have resembled the other one, And we all know that elements do not have the same behavior. If every element had hydrogen inside it, the behavior of every element would have corresponded to the other, but that's not true. So the theory got rejected. Then came the Dobnier's triad. Now, this man, he gave us a manner of classifying the elements. Okay. Now, classifying the elements in a way where he made the set of three elements, but he could only get three such sets. Okay. Now, as the discovery went ahead, a lot of elements got discovered. Okay, and they had to be classified in a uniform manner. So this was again a manner of correlating the properties, okay, where as the set of three elements were used, the atomic weight of the central or the middle element happens to be the arithmetic mean of the terminal two elements. We can see that there are only three such triads known. And as on the current date, we have 118 discovered elements. It's only future to answer to us that whether we would be artificially or naturally discovering any other more elements. So as we are moving ahead, with these theories, you must be wondering that if so many different attempts were made, okay, what was the outcome of it? Please try to understand that when these discoveries were being made, science was still in the developing phase. Okay, today we have a mechanism, we have a lot of apparatus to cross check our advancements. We have a lot of apparatus, okay, to check and to cross check whether what we are seeing or what we are having at hand, how efficacious it is to us, how useful it is to us. Whereas these people, they are creative geniuses, their minds, okay, their discoveries were happening at a time when science was not very much developed, but still with their knowledge and the potential of intellect that they held, they were able to give these correlations. Okay, so every scientist and his contribution, okay, matters to us. Okay. uh, Again, we go to the Newlands octaves. I'm sure everyone must have heard about this. Okay, he had correlated the elements in a way where every eighth element resembled the properties, and every eighth element had properties similar to the first one. Okay, but then again, to everybody's surprise, the research or the manner of correlating the property was only limited to the first 20 elements. Okay, the first 20 elements, that is until calcium. So that was the restriction that Newland's octaves had. Okay, and then the discovery of noble gases. Noble gases was something which were discovered at a much later stage, or I would say it was only after Mendeleev's, the next scientist which you will be seeing on screen. Okay, we heavily acknowledge the contribution made by Mendeleev. I think Mendeleev's manner of classification came closest to the most developed and the most advanced manner of classification that we see. Now, what we can see on the screen is that he correlated the physical and chemical properties, with the atomic masses, and this was later succeeded by Henry Moseley. Okay, Henry Moseley, the man behind the long form of the modern periodic table. It was Mendeleev's classification, okay, that came the closest to Henry Moseley's. And in fact, you when you go to read the philosophical part of the discovery, okay, you will understand that Henry Moseley clearly mentions that he drew inspiration from Mendeleev's manner of classification, that the manner in which Mendeleev had classified the elements, he drew the inspiration from that, and he went ahead to develop his manner of classification, taking inspiration and inputs from Mendeleev's classification. Okay, now what we see on the screen, okay, is the long form of the modern periodic table. I'm quite sure pretty much everyone must be aware about this. Okay, you must have heard about it. You must be knowing something about this. What you're seeing on the screen. In the very first look, I'm quite sure that many of you all must be feeling that this happens to be or looks to be a random arrangement. Okay, random arrangement of elements, or in simple words, random arrangement of substances. Okay, that is existing around us. But if we understand this diagram or this arrangement, it beautifully explains the strange pattern, okay, and the manner and the various properties and the nature in which the elements can behave and exist in nature. Now, I'm quite sure that there must be something that must be attracting your attention. You are seeing the hydrogen over here in the center, students. You're seeing the hydrogen over here in the center. I would like to highlight this thing that yes, hydrogen is an element which is placed in the center of the long form of your modern periodic table. This is the periodic table given to us by Henry Moseley. It is related to the electronic configuration of the elements. It is based on the atomic number. Henry Moseley said that the properties, be it the physical or the chemical properties of the elements, it is related to the atomic number. It was Henry Moseley who had placed hydrogen in the center of the long form of modern periodic table. And as the lecture advances, we will definitely be seeing why this discrimination with hydrogen, why has it been placed in the center. Now quite a few of you all must be wondering why hydrogen in the center. कुछ महीने पहले तक हमने 10th standard के text books में, 9th standard के text books में hydrogen for the first period and first element as the first element of the periodic table. We have always acknowledged hydrogen as the first element of the long form of the modern periodic table, but it happens to be in the center. It is not a part of the S block. Now, this is because hydrogen, it's one of the most reactive elements. It can easily combine with other elements. It is a univalent element. When I say univalent, means its valency is 1. So for every other element existing in the periodic table, it is the most sought after element, hydrogen, to combine with. Now, hydrogen, it has no group or period defined to its location. We all know that this schematic representation, its horizontal representations are known as rows or periods, and the vertical columns or groups. So this long form is divided into 7 horizontal rows and 18 vertical columns. And to take things ahead from here, we are talking about hydrogen, the most reactive element. Now, no group or period defined for its location. Now, why this discrimination is because it combines easily with everyone. It is placed in the center alone due to similarity with the S block and the P block elements. Now, pay attention to this point, students, that it can gain, lose, and share electrons. It can practically do anything and everything to achieve stability. Now, if you talk about the periodic table, elements have a fixed pattern, they have a fixed manner. Elements which share electrons, they share or in order to make bonds. Elements which lose electrons, they lose electrons in order to make bonds. And there are certain elements which gain or accept electrons from other elements in order to make bonds. I'm sure you all must be familiar with terms called as cations, anions, covalent bond, ionic bond. These are all the principles related to gain, loss, and sharing of electrons. But hydrogen happens to be one of the most wondrous elements, is because it is seen to gain, it is seen to lose, and it is also seen to share electrons with every other element around it. That is what makes hydrogen a vulnerable element. Because its property does not match completely with the S block elements, the scientists earlier thought that hydrogen would be related to the halogen family coming in the P block. But then there were properties of hydrogen which did not correspond with the halogen family as well. So in order to dissolve this confusion, because hydrogen does not match completely with the S block elements or with the P block elements, it has been placed separately in the long form of the modern periodic table. And I repeat, who has done this placement? It has been done by Henry Moseley. I'm sure you all must be coming across some doubts and some queries. I would like to mention it that towards the end of the session, we will be entertaining your doubts. You will be getting answers to the questions that you all are having. So please make a note of it. You all can also share your email IDs along with your doubts so that we can get back to you with the solutions and the answers to your doubts in the later part of the day. Now, taking things ahead, hydrogen, please remember that it's a colorless, odorless, and a tasteless gas. It's a highly flammable gas, and it burns with an invisible flame. Now, hydrogen has been used in the okay, hot air balloons. Okay, now this, the reason behind this is the lightest gas to exist. It expands very easily on heating. Okay, and taking inspiration from this, okay, we have been using hydrogen as a source of fuel in the rockets. Okay, there are layers and jackets of hydrogen filled up and pumped up into the rockets that go into the space for the research. Okay, and one of the most important reasons for that being is that hydrogen is a non-polluting source of energy. It is high on the energy quotient, and it's a non-polluting source. We all know that pollution is a problem that we need to tackle. Okay, in the day of life, we need to get rid of the pollution, and hydrogen happens to be one of the elements, okay, which is providing us energy and pollution free energy. uh, it's also mixed in petrol, okay, which is used as a source of fuel and energy to enhance its combustibility. Okay, any fuel, students, remember, any fuel, when it burns, it releases carbon dioxide and certain other oxides. Burning is nothing but a reaction with oxygen. When you say burning, what must click to your mind in the very first place is that it is a reaction with oxygen. Okay, now this reaction with oxygen, okay, it will release certain oxides, it will release certain other elements. Okay, and in order to ensure that a substance as a source of energy and fuel getting combusted completely, we mix it, we mix hydrogen in petrol in order to ensure that the complete combustion happens and that no poisonous gases are being released into the atmosphere when any kind of fuel is being combusted as a source of energy. Now, moving ahead, we come to the S block elements. We come to the S block elements. Now, the S block elements, this is the very first section of the periodic table. These are two separate groups. Okay, when we talk about the group one, that's called the alkali metals, and the second group, okay, that's the alkaline earth metals. Okay, why alkali and why alkaline is because they show a strong tendency to form bases on reaction with water. These elements and their oxides react with water to form bases. Okay, now they are electropositive in nature. Okay, quite a few of you all must have heard this term electropositive. Okay, what it means is that these elements show a tendency to lose electrons. Okay, they show a tendency to lose electrons and form cations. What you can see over here is sodium losing an electron to become an Na plus, and calcium losing electrons to become Ca2 plus. So the very first group happens to be the monovalent, and the second group happens to be the divalent. By monovalent, we mean the valency is 1, and by divalent, we mean the valency is 2. Now, going ahead, the S block elements, they form salts with halogens. You can see it as an example. We saw it earlier in the lecture as well. NaCl, sodium chloride, it's a salt. Correspondingly, similarly, calcium chloride is also a bivalent salt of calcium and a halogen, that's chlorine. Okay. Now, as I mentioned earlier, they react with the hydroxyl group. There is the OH group to form bases. To give you examples of that, NaOH happens to be a base. CaOH twice also happens to be a base. So the bases that we are getting from the S block elements, okay, they are strong bases. And to emphasize more, the bases of alkali metals are stronger than the bases of alkaline earth metal. That is the group one, that is lithium, sodium, potassium. Okay, these elements combine with the OH group to give you strong bases. And likewise, you get MgOH twice, a CaOH twice, that is magnesium hydroxide, calcium hydroxide. These are bases, but not as strong as the bases of group 1 elements. Now, another important thing is that the S block elements, okay, they combine with the halogens or the salts, okay, to form salts, and these salts act as the electrolytes, okay, that happen to conduct electricity. Now, what you're seeing on the screen now is the general configuration that happens to be NS1 to 2. Okay, NS1 to 2, we read it as NS1 to 2, where N corresponds to the number of the orbit, okay, where the configuration of the particular element will end, and S happens to be the subshell. Okay, now subshell is an inner classification of the shell or the orbit which we will be understanding in more detail when we do the topic structure of atom in the subsequent lectures. So the configuration for an s block element will always end on the s subshell of the orbit. The configuration will always end on the s subshell with respect to its electronic configuration, and the number of electrons would either be 1 or 2. Now, to remember, the s block elements are also known as the soft metals. Okay, the s block elements are also known as the soft metals. I hope that those of you all who wish to are noting down the things, because these are those points which will definitely help us as we proceed ahead with our syllabus of chemistry, and things that we need to know with respect to the entire syllabus of chemistry. Now, moving ahead, we go to the other section of the periodic table that's called the D block elements. Now, what you look at the screen is an arrangement of 40 elements. Okay, now this happens to be the biggest section, okay, or the largest section of the long form of the modern periodic table. Okay, now these elements are also known as transition metals. Okay, the very first group is also known as the first transition series. Okay. The second one, it's called the second transition series. Now, what we need to highlight or what we need to remember is that the first transition series is the fourth period of your periodic table. The first transition series is the fourth period of your periodic table. The D block elements do not hold elements in the first three periods. Okay, they do not have elements. We do not have elements rather for the D block in the first three periods. The D block comes into existence from the fourth period onwards, and that's also known as the first transition series. Taking things ahead, the fifth period, okay, of the D block, that's called as the second transition series. The sixth one, it's called the third transition series, and it's also called as the post-lanthanoids. Now you can see a gap over there mentioning 57 to 71. Now those are those elements which are placed slightly separated from the main body or the main structure of the periodic table. That's called the lanthanoids. Okay, that is 57 to 71. Why they are placed separately, we will be understanding that later. So the third transition D block, it's also called as the post lanthanoids, and the fourth transition series, it's also called as the post actinoids. Okay, because again over there we can see 89 to 103, that is the series of actinoids, which is again separated from the main structure. Why this lanthanoids and actinoids have been placed separately, we will be understanding that soon. So points to be noted over here is that the first period of the D block happens to be the fourth period of your periodic table. That's also called as the first transition series. The second one is the fifth period of the periodic table. That's called the second transition series, and then correspondingly the sixth period called the third transition series, and the fourth one or the seventh period of the D block, that's called the fourth transition series. Okay, now why these elements are called as transition metals? Why are they called as transition metals? Is because their last two orbits are incomplete. Okay, their last two orbits are incomplete. Remember, students, okay, that we are generally accustomed to seeing elements having an incomplete outermost orbit, but with respect to D block, we notice that these elements have last two orbits as incomplete, and that is what makes it the transition. That is what makes it called as the transition elements. Now remember that transition means a change that is not related or influenced, okay, by any other element. Okay, when we say that a change is influenced by any other element, it's called a reaction. Okay, for sodium to change its manner of existence, okay, it has to depend on the other element with which it is going to react with. But in case of the D block elements, their last two orbits are incomplete. Okay, they have some empty space in their last two orbits. due to which their electrons can shift, they can change their location. And because they can change their location, their nature also changes. Okay, understand this thing, that, understand that uh, the transition element, okay, or the nature and behavior of the element depend on its valency, the number of electrons that are present in the last orbit. Okay, now this valency, or this number of electrons in the last orbit, it can change in the d block elements on their own. They can shift their electrons, due to which their value of valency will change. I'm sure you all must be knowing, okay, that the element like carbon, it has a fixed valency of 4, oxygen has a fixed valency of 2, sodium has a fixed valency of 1. When you talk about the d block elements, okay, the d block elements, these are elements, okay, with metals, and these metals, they can change their value of valency. Now, taking it ahead, these elements have their last 2 orbits incomplete, and that makes it the more characteristic. And they are all hard metals with a few exceptions. Over here we have mercury. Okay, mercury happens to be a metal, but it's in the room temperature. We notice that it is existing in the liquid state. Okay, now understanding metals in a slightly deeper and a better manner, I would say that this term metal, okay, it holds on to all the major properties that metals exhibit. Okay, when we talk about metals, with M comes malleability. Okay, I'm sure you all must have heard this word, malleability. Malleability is the ability to draw the metals into fine sheets. Okay, you must have heard this term as malleability and ductility. Metals are malleable and ductile. So malleable means that the metals can be made into sheets, into fine sheets. You can melt them, you can flatten them, you can hammer them into flat sheets. And for everybody's knowledge, we should know that aurum, or gold, now aurum happens to be a chemical name for what is known as gold. Okay, Au happens to be its syllabus. It's the most malleable metal, and also platinum. Okay, now, if you talk about the entire periodic table, the order of malleability, please make a note of this. It goes as, okay, the S block is slightly lesser than the P block, but you will notice that the D block over there is greater than all of the other blocks of the periodic table. The S block, the P block, the D block, and the F block. Okay, the D block happens to be greater. The order of malleability for the D block elements happens to be the highest. Now, taking things ahead, E, the metals, it stands for the elastic nature of metals. Okay, metals are electropositive in nature. They are good conductors of heat and electricity. So again, E helps us to remember that metals are elastic, they are electropositive, they show tendencies to lose electrons. Okay, T explains the tensile strength. Tensile strength basically means the ability to stretch and expand on being overloaded with weight. So metals have this ability to stretch and expand, so that the weight distribution happens over the mass of the metal. And so that's called the tensile strength. Again, the most tensile elements happen to be gold and platinum, which are elements of the D block, and least tensile element happens to be plumbum or lead, which is an element of the P block. Okay, now, again, another important property of the metal happens to be alloy formation. We see so many different alloys, being used around us. And certainly alloy, what does alloy do? It basically enhances the utility of a metal. Many metals are there which may not be as useful to us as in their independent form, but when mixed with certain other elements, their utility and our ability to basically use them increases. Also, alloy formation enhances the hardness or the toughness of the metal. Okay, now we all know that metals are sonorous. Sonorous means the ability to produce sound, and we are aware that every metal, when it comes in contact with any other surface, or when it is hit with some other substance, it produces a unique different sound, okay, which is characteristic to that particular metal. Now, Understanding the electropositive nature of the metal, what makes the metal more usable and more important to be understood as an element is its electropositive nature. Now, metals show the tendency to lose electrons. Okay, you all must have heard this term reduction and oxidation in your lower standard, boys and girls. Okay, losing electrons means oxidation. Okay, and metals undergo oxidation. Metals lose their electrons. Okay, and they have a tendency to form cations. They form positive ions. So they lose electrons and they act as reducing agents. The electron which is lost by a metal is certainly gained or accepted, okay, by some other element. So the other element gains the electron. A loss of a metal is a gain of some other element, and gain of electron is termed as reduction. So it is metal which is losing the electron, the metal which loses its electron, and the other element gains it up. So that is called as the reducing agent. Metal helps other elements to gain electrons. And what we can see here on the screen is a simple reaction explaining the same phenomena. We can see that zinc, it is losing 2 electrons to become a divalent cation, that is a positive ion, that is Zn 2 plus. So electropositive nature of metals is something which we need to emphasize on and remember it with respect to an electropositive element and its electropositive nature. So that is with the D block and the electropositive nature of the metals. I hope you all are noting down the things. Okay. Now, going to the next block, that's called the P block elements. Now, what you see on the screen is the arrangement of the elements which are identified as the P block elements. And one more addition to this thing happens to be this, the noble gas group. Okay. Now, the most vulnerable group of the entire periodic table happens to be the P block. Okay. We will be definitely paying more attention to this section of the P block in the entire span of 2 years that you would be spending in science in your 11th and the 12th standard. And what makes it so important to be understood as a section of the periodic table is that this section of your periodic table actually does not match with the actual statement of the periodic table itself. What does the periodic law state? That the position and the properties of the elements, it's a characteristic feature of its atomic number. Now, going by this definition, what do we mean? We mean that similar elements, okay, will be placed together. Elements showing similar properties, elements showing the same nature and pattern of behavior will be placed together. But to everybody's surprise, you will notice that in the P block elements, all the different categories of elements come together. It's all the different categories of elements coming together. It's the metal, the non-metal, the metalloid, the halogen, the radioactive element. Now, we never saw this thing. We are not noticing any such phenomena in the other groups of the periodic table. When we talk about the S block elements, they are all soft metals having a uniform manner and behavior and a nature of existence. When we talk about the B block elements, they are all the hard metals. But when we talk about P block, okay, a slight query comes into our mind, because under a metal, you will see the other element, which is a non-metal. Around a non-metal, you will see another element, which is a metalloid. Okay, around the halogen, you must be seeing the halogen group. Everybody must be quite familiar to the halogens. It's called the fluorine, chlorine, bromine, iodine. You are seeing just beside that halogen to its right is the noble gases. That's the most stable element. That's a stable group of elements. So beside the most unstable is the most stable. Now, isn't it contradictory to what we have been hearing in the periodic table, that similar elements are coming together, but here it's all put together, but all are different from each other. But still, if they are different from each other, तो Henry Moseley ने ऐसा क्यों किया? उसने location change क्यों नहीं किया? That's because, guys, he wanted to maintain the uniformity. Okay, when you look at these elements, they follow a similar pattern of their electronic configuration. He wanted to maintain the uniformity, something which the others had failed at, maintaining the uniformity. And Henry Moseley wanted to ensure that the uniformity of the elements are being maintained, and that is the reason wherein even if the elements were showing certain different nature, certain different properties, थोड़े अलग properties भी मिल रहे थे, थोड़ा सा different manner of behavior and existence भी मिल रहा था, तो भी elements को साथ में रखा गया, because of their similar electronic configuration. Now, emphasizing on the p block elements, you have elements coming in a group 13 to 18. Okay, now this is a group with 37 elements, the second largest group of your periodic table. Okay, the group number 13, that's called the boron family. The group number 14, that's called the carbon family. The group number 15, that's called the nitrogen family. The group number 16, that's called the oxygen family. 17, that's called the fluorine family. It's also known as the halogen family. Okay, and then the last group, that's called the neon family, or the noble gases, or the inert elements. Okay, now this 18th group, or the neon family, it's also called as the zero group. Now, why is it called the zero group? Everybody must be thinking about, why do we call this the zero group? It's group number 18. We must call it group 18. Why the zero group? Because the major factors, or the governing principles of reactivity, that is valency, okay, that is the oxidation state, reactivity of these elements which come under the neon family, or the noble elements, or the noble gases, it happens to be zero. Okay, they have a stable outermost orbit configuration. They are not in search of stability. In fact, all the other elements of the periodic table, except for the noble gases, are in search of stability. The noble gases happen to be the stable elements. They do not wish to combine with other elements. They are inert elements. They provide us with a non-reactive inert atmosphere. Okay, and that's why they are called the zero group, because the valence which controls the reactivity of an element, okay, that happens to be zero, and that's the reason why they're also termed as the zero group. Now, this block, the p block, as I told you, it contains elements that are metals, non-metals, metalloids, halogens, and radioactive elements. All of these have different characteristics, different manners, and they are still put together. The properties over here, okay, of boron, the very first element, you can see that boron with number 5, carbon with number 6, nitrogen with number 7, oxygen with number 8, fluorine with number 9. Okay, now there are certain other elements below it. Boron, okay, down boron you will see aluminum, gallium, indium, thallium. Now the properties of boron does not match with aluminum, gallium, indium, and thallium. Properties of carbon does not match with silicon, germanium, stannum, plumber. They are all elements belonging to the same group. They are all elements belonging to the same pattern of arrangement, but then they don't show similarity in their properties. If they are placed together, they should have shown certain similarities, but they don't. In fact, their properties are completely contradictory to each other. If we talk about oxygen, it shows a behavior that's completely contradictory to the nature of sulfur, selenium, tellurium, polonium. Okay, polonium happens to be a radioactive element. Okay, nitrogen happens to be a non-metal. Bismuth happens to be a metal. Okay, so these are the variations. Okay, this is what makes this section of periodic table a characteristic section, because the properties of the elements do not match with the other members of their own group. Okay, now going ahead, you can see the electronic configuration. It is important to note that the electronic configuration of the p block elements will end or terminate on the p subshell of their outermost orbit. Okay, on the p subshell of their outermost orbit, as I mentioned earlier. Okay, subshells are part of shells. Okay, subshell is a inner classification of what's also called as the orbit. Okay, we will be definitely dealing with this thing in detail when we do the topic structure of an atom or atomic structure. Okay, so as of now, the general electronic configuration for the p block elements happens to be ns2, that is the s subshell that's been completely filled up, and the p subshell, which is incomplete, which may have electrons between 1 to 6. Okay, now going to the f block elements. Okay, a separate section. We discussed something about this earlier in the d block as well. Okay, the f block elements. Now this is also called as lanthanoids and actinoids, these two separate series of 14 elements each. Now, why did the scientific fraternity, or why did Henry Moseley, to be in specific, and along with him the other group of scientists as well, supported the idea or the thought of having these elements placed separately from the main structure of the periodic table? Why is it being separated from the main body of the periodic table? Is because these elements show a specific peculiar character, that they have an unstable nucleus. Yes, students, you are hearing it right. These are elements with an unstable nucleus. All of your S block, all of your P block, all of your D block, except for the noble elements, have an unstable outermost orbit. They have an unstable outermost orbit. But these, the F block elements, are a group of elements which have an unstable nucleus. And we all know that the nucleus does not participate in bond formation. Okay, so the only way left for these elements, to achieve stability is to break, is to disintegrate, is to repeatedly keep on breaking on their own in order to achieve stability, or in order to become stable. Okay, you all must be wondering that we are not very familiar, with these elements of F block. We haven't heard this name before, called as lanthanum, cerium, praseodymium, neodymium, promethium, samarium, gadolinium, and other such elements. But then, what is also important to be understood is that these elements do not actually participate in reactions. They don't react with other elements in order of stability. Okay, so going ahead, they are also termed as inner transition metals because they provide transition in the sixth and the seventh period. We saw it earlier that these elements were called uh, um, they are termed as inner transition elements. Okay, they correspond to the sixth and the seventh period of the periodic table. Okay, that is why we call them the post-lanthanoids and the post-actinoids. The sixth period of the periodic table, that is the D block, it's called the post-lanthanoids, and the seventh one is called the post-actinoids. Okay. Now, the first series of these elements, the lanthanoids, they include elements with atomic numbers 57 and ending at 71. You can see that over here. They start with 57 and ending at 71. Okay, and then the second series happens to be the series of elements with actinides and include elements with atomic numbers beginning from 89 and ending to 103. Okay, now this is about the lanthanoids and the actinoids. Okay, now remember that the lanthanoids are non-radioactive. They are slightly stable. Okay, they are slightly stable. They are non-radioactive, but they are slightly stable. Actinoids are known to be radioactive in nature. Okay, I hope you are following the things, okay? And I'm quite sure that if you'll have any doubts, you would be mentioning them. And towards the end of the session, we will be discussing each of your doubts as far as possible. So this is with the entire section of the periodic table. Okay, we saw the S block, we saw the P block, we saw the D block and the F block, how these elements, okay, having different set of properties and manner of existence and nature and reactivity are all put together and existing around us. Now, what are the salient features of the modern periodic table? Now, over here, we have the elements that are placed in 7 horizontal rows, okay, and 18 vertical column called as groups. The elements belonging to the same period, they have the same number of shells, which is equal to the period number. Okay, so the number of orbits that an element has, the number of orbits that an element has, okay, will determine the period to which that element belongs. And in each period, the number of electrons in the outermost orbit will start from 1 and end with an element of the 0 group. Okay. So that is with respect to the basic section of the periodic table, that is the different blocks of the periodic table, that is the S block, the P block, the D block, and the F block. Now, going ahead, what do we mean by this term periodicity? Okay, it means the recurrence of similar properties of the elements after certain regular interval in the manner in which they are arranged. That is the manner of increasing atomic number. Okay, the recurrence of similar properties of elements after certain regular interval. Okay, when they are arranged in the order of increasing atomic number. Now, the different trends that we notice in the periodic table, they are the atomic size, the metallic character, the ionization enthalpy, the electron gain enthalpy, electronegativity, and valency. Now, I'm quite sure you all must have heard these terms, or you all must have come across these terms. We'll just try to understand them in a detailed manner. Talking about the atomic size, students, we notice that the atomic size increases when we move from right to left in the periodic table, and it increases from top to bottom as the number of orbits are being getting added. Okay, what you can see over here is that an element with just one single orbit having a smaller size and a single electron, but as the number of electrons are increasing, so is the number of orbits. Okay, as the number of electrons increases, you can see that the number of orbits goes on increasing. The electrons are less, the orbits are less, the electrons are increasing, and the orbits are also increasing. So the atomic size, it increases down the group. Okay, and it also increases from right to left as we move across a period in the periodic table. Going ahead to the metallic character deals with electropositivity. So the metallic character decreases as we move from left to right across a period. The metallic character decreases as we move from left to right across a period. The metallic character is seen to increase from top to bottom down a group. The metallic character is seen to increase from top to bottom down a group. And the metallic character, it follows this trend because down the group positivity increases. Okay, if we have a look at this image, it makes it more clear for us to understand the gradation of the metallic character, that the non-metallic character will increase as we move up, the metallic character will increase as we move down. Okay, electrical conductance, in other words, means the metallic character, and the metallic character is known to increase when we move down the group. Now, going to ionization enthalpy. Okay, it is the amount of energy required to eliminate an electron out of the outermost orbit of an atom. Okay, amount of energy required to eliminate an electron out of the outermost orbit of an atom. Now, with an addition of the orbit down the group, as we move down the group, children, as we go down, what happens is the number of orbits goes on increasing. Now, when the number of orbits goes on increasing, what happens is that the electron are going away from the nucleus. So you notice over here that an electron present in a bigger orbit, in an orbit which is away from the nucleus, it's easier for the atom to lose this electron. It is easier for this atom to lose this electron because we noticed that the electron was in a region which is quite away from the central nucleus. So losing that electron was easy. But when we talk about the elements or the atoms having a smaller atomic size, okay, for them to lose the electron is not easy because the nucleus has held it strongly. The electrons are in a region which is closer to the nuclear influence, and the electrons are held tightly. So it takes a time, but then it loses. So the energy required to eliminate an electron from an orbit which is closer to the nucleus, okay, it is difficult to eliminate that electron. Going ahead, electronegativity. It is defined as the tendency of an atom to attract the shared pair of electron close to itself after it has entered a covalent bond. Now, covalent bond means a bond where the electrons are shared equally between the two atoms. Okay. Now, what generally happens is that if these atoms bear a difference in their electronegativity values, okay, uh, electronegativity value explains the tendency of an atom to hold an electron. So you can see that the atoms have shared an electron, but then an element having a higher electronegativity, it happens to pull the shared pair of electron close to itself. And that's precisely the reason why the distribution of electron between the two atoms gets disturbed, leading to development of partial charge on the atoms that are present in the covalent bond. To sum it up, guys, this is a table that gives us a fair idea of the manner in which the trend behaves with respect to our periodic table. You have the ionization energy, which is increasing as we move from left to right. You have the electronegativity, which is increasing again from left to right. There is electron affinity, or the tendency to attract electrons, okay, which is increasing from bottom to top. The atomic radius decreases from top to bottom. You have the atomic radius increasing from the, there is electronegativity, which is increasing from bottom to top. So that is it with respect to the periodicity or the trends in the periodic table. Here you have an image which is summing up the nature of the elements with respect to the trends, that is the atomic radius, the melting point, their electronegativity, ionization energy. Of course, we will be dealing with these properties in detail in our subsequent lectures and sessions to follow. Okay, that is it for the session.